have you ever carried a bucket of water up the stairs and felt how much effort it took? That effort isn't wasted, it's stored in the water as energy. That's gravitational potential energy in action. Whenever we lift an object above the ground, we're actually storing energy in it. This energy is due to its position in the Earth's gravitational field, and we call it gravitational potential energy. The more you lift, the more energy is stored. And when the object falls, this energy gets released. So gravitational potential energy is the energy a body possesses because it is elevated in height, and it gives the body the potential to do work. Let's now define it properly. Gravitational potential energy is usually denoted by capital U. It depends on three things: the mass of the object, the height it is raised to, and a gravitational pull of Earth. We calculate it using the formula U equals m into g into h, where U is the potential energy in joules, m is the mass in kilograms, g is the gravitational acceleration, which is 9.8 meters per second squared, and h is the height in meters. So, lifting a 2-kilogram object to a height of 3 meters would store U equals 2 into 9.8 into 3. That is 58.8 joules of potential energy. Let's derive the formula to understand it better. We know that work done is equal to force into displacement. Now, the force needed to lift a body vertically is equal to its weight. Weight is mass times gravitational acceleration, or F equals m into g. The displacement is the vertical height, so we substitute. Work done W equals m into g into h. And this work done, it's stored as potential energy. Therefore, we conclude gravitational potential energy, U equals m into g into h. One important thing to understand, potential energy is relative. We always need a reference level where we say energy is 0. Usually, we choose the ground or floor as this reference. So when a body is at the ground level, we consider its gravitational potential energy to be 0. As you raise the object higher, its energy increases. As you bring it down, its energy decreases and reaches 0 again at the base level. This assumption helps us compare energy changes with ease. Now let's talk about how gravitational potential energy changes. Suppose a body is raised from height h1 to height h2. Its gain in energy is given by delta U equals m into g into open bracket h2 minus h1 close bracket. But if the body falls from h2 to h1, the potential energy is lost. In this case, delta U equals m into g into open bracket h1 minus h2 close bracket. Whether rising or falling, the change in gravitational potential energy depends only on the vertical height covered, not the path taken. Gravitational potential energy, or GPE, plays a vital role in our daily lives and in major engineering systems. Whenever an object is raised to a certain height, like a lifted weight, a rock on a ledge, or water stored in a tank, it gains gravitational potential energy due to its position above the ground. One of the most practical uses of this energy is in hydroelectric dams. Here, water stored at a height is released to flow downward, and this movement is used to turn turbines and generate electricity. Even thrill rides like roller coasters rely on gravitational energy. After the ride is pulled to the top of the first hill, it uses GPE to power the rest of the motion through loops and drops. Understanding gravitational potential energy is essential in fields such as civil engineering and mechanics, where energy storage, transfer, and structural safety are closely tied to height and weight. Overall, GPE helps explain how energy is stored and transformed in vertical motion. Whether it's water falling, an object dropped, or a building designed to hold loads at height. Let's wrap up everything we've learned about gravitational potential energy. Gravitational potential energy, or GPE, is the energy a body possesses due to its position in a gravitational field. Simply put, because of its height above a reference point. The formula to calculate it is U equals m times g times h, where U is the gravitational potential energy in joules, m is the mass in kilograms, g is the acceleration due to gravity, and h is the height in meters. This energy depends directly on both mass and height. The heavier the object, or the higher it is raised, the more potential energy it stores. When an object gains height, it gains energy. When it loses height, it loses energy. So the energy gained or lost is directly proportional to the change in vertical height. Usually, we consider Earth's surface as the reference level, and we define the gravitational potential energy to be 0 at that point. Making calculations consistent and meaningful.